We all rely on batteries. I mean, every single day, right?
Yeah.
From the moment that alarm goes off
Yeah.
to that last check of, whatever before bed.
Definitely.
But beyond just powering our phones and gadgets, the actual science, the engineering behind battery tech,
Yeah.
it's surprisingly deep, really dynamic field.
It absolutely is.
So today, we're diving into some material. One of you sent in Slobodan Petrovic's battery technology crash course. We're going to really get into the hood of this essential tech.
Exactly. And our goal here, our mission for this deep dive, is to move beyond just, knowing batteries power things.
Right.
We want to really understand the fundamental principles. How do they actually work? We'll look at the core mechanics, the different kinds out there, and the key factors that determine how well they perform.
And it's kind of mind-boggling when you think about the range, isn't it? You've got tiny microscopic devices all the way up to huge installations storing energy for, whole cities.
It's incredible.
That versatility alone tells you there's some serious ingenuity involved. Okay, so Petrovic starts with the basics. How do these things actually make electricity? Let's get into it.
Well, one interesting thing right off the bat is that a battery, it directly changes chemical energy into electrical energy. It uses these electrochemical reactions.
Okay.
Now, that's different from, say, a traditional power plant. Those often involve heat, then mechanical energy, then electricity, like a thermal engine.
Right.
And those thermal processes, they have limits on their efficiency, something called the Carnot cycle. Batteries, though, because they're direct chemical to electrical, they have the potential for much higher energy conversion efficiency.
So no tiny steam engines inside our phones then?
No, not quite.
Makes sense. Now, Petrovic talks about redox reactions being the engine of the battery. Can you break that down for us?
Absolutely. Redox, it's really at the heart of it. It's actually two things happening together, reduction and oxidation. Oxidation is where a material loses electrons. That happens at the anode, typically the negative terminal in discharge.
Loses electrons.
Got it. And reduction is the opposite, where a material gains electrons. This happens at the cathode, usually the positive terminal.
Gains electrons.
Petrovic uses the lead-acid battery as a classic example. In figure 1.4, you can see during discharge, the lead at the anode, it loses electrons, it gets oxidized and turns into lead sulfate.
Okay.
And at the same time, the lead dioxide at the cathode, it gains electrons, gets reduced, and also becomes lead sulfate.
So underneath it all, no matter the battery type, it's this basic dance, this exchange of electrons creating the power.
That's the core concept, yeah.
But Petrovic makes a point that not all redox reactions are electrochemical, like burning wood, he says. What's the key difference that makes a battery? Well, a battery.
That's a really crucial distinction. Yeah, burning wood is a redox reaction. Carbon oxidizes, oxygen reduces, you get heat and light. But it's not electrochemical because there isn't an electrolyte. You need that special medium to carry charged particles, ions, between the reaction sites. And in a battery, those sites, the anode and cathode, they're physically separated. That separation plus the electrolyte is key.
Okay, so it's that specific structure that channels the electron flow properly. What are the must-have parts for this setup?
You need fundamentally two electrodes, the anode and the cathode.
Right.
They need to be in contact with an electrolyte, which is this substance that conducts ions, not electrons, but ions.
Right.
And then critically, you need a separator. It's usually this thin, non-conductive material physically placed between the anode and cathode.
To stop them touching?
Exactly. Prevents a short circuit. But it has to be porous enough or designed so ions can still travel through it from one side to the other.
Okay, anode, cathode, electrolyte, separator. Got the components. So how does it all work together when I, plug my phone in or turn on a flashlight?
Okay, so during discharge, when you're using the battery, those electrons freed up at the anode by oxidation. They can't go through the electrolyte, so they travel through the external circuit. That's the wire, the device, whatever is connected. They go to cathode.
Right.
Now, to complete the circuit inside the battery, you need charge balance. So positively charged ions move through the electrolyte, through the separator from the anode side towards the cathode side.
Okay, so electrons outside, ions inside.
That's the discharge flow. Now, when you recharge it using a power supply, you're basically forcing everything to go backwards. Electrons are pushed onto the anode, ions move the other way through the electrolyte.
Right.
And interestingly, Petrovic points out something important using the lithium-ion example in figure 1.6. The electrode identities, which one is the anode, negative on discharge, and which is the cathode, positive on discharge, they stay the same. It's just the direction of the flow that reverses during charging.
Oh, okay, that's a good point. The roles don't flip, just the traffic direction.
Precisely.
Now, Petrovic gets into predicting voltage. He mentions standard reduction potentials, but then says the Nernst equation is more realistic. Let's unpack that.
Yeah, this is interesting. We can actually calculate a theoretical voltage for a battery cell, but under very specific ideal conditions.
Standard conditions.
Exactly. Standard reduction potentials are measured at a specific concentration, usually 1 molar, and at 25 degrees Celsius. You look up the values for your anode and cathode materials, do a simple calculation, and get a standard cell voltage.
And Petrovic gives some examples, like lithium and fluorine, almost 6 volts.
Yeah. Theoretically, that pairing could give a huge voltage. It shows the chemical potential that's out there.
Wow. But real batteries aren't usually operating at exactly 1 M concentration in 25 degrees C, are they?
Almost never. And that's where the Nernst equation comes in. You can see it in figure 1.8. It's a formula that adjusts the voltage prediction based on the actual concentrations of the reactants and products inside the battery at that moment, and also the operating temperature.
Okay, so it's more dynamic.
Much more dynamic. For lead-acid batteries, for instance, the Nernst equation shows that the voltage is higher when the sulfuric acid concentration is high, like in a fully charged battery.
Makes sense.
As it discharges, the acid gets used up, its concentration drops, and the equation correctly predicts a lower voltage. So the key thing for you to remember is battery voltage isn't fixed. It changes.
So the electrolyte, it's not just sitting there passively letting ions through, it's actually involved.
In many types, yes, it's an active participant. Think lead acid again, sulfuric acid is consumed and produced.
Right.
Same for nickel-cadmium with its potassium hydroxide electrolyte. Petrovic even notes in figure 1.9 how sulfuric acid's conductivity changes with concentration.
Interesting.
And with nickel-cadmium, the potassium hydroxide might be less conductive than sulfuric acid, but it can sometimes allow for faster electrode reaction.
Okay, but not always. What about lithium-ion?
Lithium-ion is different. The electrolyte there, often something like lithium hexafluorophosphate dissolved in an organic solvent. Its main job is just to shuttle lithium ions back and forth. It doesn't really get consumed or produced in the main reaction. Table 1.1 actually gives a good comparison of ionic conductivities for different electrolytes.
Okay, that clarifies things. Petrovic also mentions thermodynamics. Gibbs free energy? How did that fit in?
Yes, Gibbs free energy. It's a fundamental link. Equation 1.2 shows a direct relationship between the change in Gibbs free energy for the battery's reaction and the cell voltage.
How so?
Essentially, a spontaneous reaction like a battery discharging naturally has a negative change in Gibbs free energy. This corresponds directly to a positive cell voltage. The bigger the negative change in energy, the higher the voltage, basically.
I see.
And the voltage also depends on how many electrons are transferred in the reaction. Petrovic uses examples 4 and 5, looking at alkaline and zinc chlorine batteries to show how you can use these principles to calculate key battery parameters. It connects the chemistry to the electrical output.
Okay, voltage makes more sense now.
Yeah.
Let's talk capacity. How much energy can a battery actually hold? Petrovic starts with theoretical capacity.
Right, theoretical capacity. It's usually measured in ampere hours. It represents the maximum amount of electrical charge a battery could possibly store if all of its active material reacted perfectly.
If everything worked 100% perfectly.
Exactly. And it's directly related to the amount of active material you have based on Faraday's first law of electrolysis. Basically, a certain amount of stuff can hold a certain amount of charge.
Okay. And amp hours isn't energy though, right?
Correct. Amp hours is charge. To get energy, usually measured in watt hours, you multiply the charge capacity by the battery's voltage, V. So theoretical energy is theoretical capacity times theoretical voltage.
And this leads to those important specs we always see, specific energy and energy density.
Precisely. Specific energy tells you how much energy you get for a given weight. It's usually in watt hours per kilogram, WH/kg. How much energy is packed in per kilo?
Right. More energy, less weight is good.
Generally, yes. And energy density is similar, but for volume. Watt hours per liter, WHL. How much energy can you cram into a certain space?
Okay.
That zinc chlorine example Petrovic mentions, with a theoretical specific energy of 835 Wh/kg, that's huge. It shows the chemical potential.
Yeah, 835 sounds amazing.
Yeah.
But there's always a but, isn't there? What's the reality check?
Absolutely. There's a big gap between theoretical and practical. That lead-acid battery example again. Theoretically, maybe 244 Wh/kg. practically. You're looking at maybe 35 weight kHm.
Wow, that's a massive difference. Why?
Well, a few reasons. First, the battery isn't all active material. You've got the casing, the current collectors, the separator, the electrolyte itself.
Yeah.
All that adds weight and volume, but doesn't store energy. It's like packaging.
Right, the overhead, the non-energy parts.
Exactly. Petrovic shows this for nickel-cadmium in figure 1.10. And then you have electrochemical losses.
Losses, like
Yeah. Things like the reactions not being perfectly efficient or fast. Not all the active material might actually get used, especially at high discharge rates. And there's internal resistance like friction for the electrons and ions, which wastes energy as heat.
So you only get a fraction of the theoretical potential.
Typically, yeah. Maybe 25–35% is a rough ballpark for many systems. Table 1.3 compares practical specific energy for different types. Lithium-ion usually comes out higher than lead-acid or niacid.
Which is why it's popular for phones and EVs.
Right, though still lower than, say, fuel cells. But the table also points out that something like nickel-cadmium can still be better for really high-power applications, even if its energy storage isn't top tier.
Power versus energy. Okay, so how do we actually measure how real battery performs? Testing.
Yeah, standard testing involves discharge cycles. You charge it up, discharge it while measuring how much charge comes out, then charge it again. Repeat, repeat, repeat.
Hundreds or thousands of times.
Often, yeah. You track how the capacity holds up over those cycles. Ideally, you want it to stay close to the original capacity for as long as possible. Figure 1.12 shows typical voltage curves during a discharge test.
Okay. And we hear terms like DOD and SOCI all the time. Depth of discharge, state of charge. What's the deal there?
Good question. Depth of discharge, DOD, is simple. It's the percentage of the battery's total capacity that you've used. So 50% of EB means you've used half the charge.
Okay.
State of charge, SOCI, is the opposite. It's how much capacity is left, usually as a percentage of the initial rated capacity. Figure 2.1 shows they're just inverse concepts. SOCI equals 100% of DOD.
And why specify initial rated capacity?
Because as we just discussed, a battery's actual capacity fades over time in cycles. So if you just measured SOCI relative to its current diminished capacity, you wouldn't get a true picture of its health. You need to compare it back to what it could hold when it was new.
Gotcha. And often end of life is defined as, what, 80% of that initial capacity?
That's a very common definition, yes. Once it can only hold 80% of its original charge, it's often considered worn out for its primary application.
Now, thinking about charging, the voltage doesn't just stay flat while you charge, right?
No, definitely not. Figure 2.2 shows a typical charge profile. The voltage climbs, and there's a critical upper limit.
A limit you shouldn't exceed.
Absolutely. Pushing the voltage too high during charging is dangerous. It can cause overheating, maybe even thermal runaway.
Which sounds bad.
It is bad. Can lead to fires or explosions. In batteries with water-based electrolytes like lead acid, overcharging causes electrolysis splitting water into hydrogen and oxygen gas.
Okay.
In lithium-ion, with their organic electrolytes, overcharging can break down that electrolyte, also producing gas and heat. Thermal runaway is especially risky in sealed cells where that heat and gas can't easily escape.
Right, pressure builds up.
Okay.
Petrovic gives an overview of different rechargeable systems in Table 2.1. Any key patterns there?
Yeah, you notice some trends. The anode, the negative electrode during discharge, is often a pure metal in its zero valence state. Lead, cadmium, lithium.
Oh, yeah?
Nickel metal hydride is a bit different, using a metal alloy that absorbs hydrogen. And the cathode positive on discharge is frequently a metal oxide. Lead dioxide, nickel oxyhydroxide, lithium cobalt oxide, things like that.
Makes sense.
Table 2.2 then focuses on alkaline systems. It highlights potassium hydroxide, KOH, as a really common electrolyte, even though it's less conductive than sulfuric acid.
Why use it then?
Often because it allows for faster reactions at the electrodes or provides better stability for certain electrode materials. It's also interesting that manganese dioxide, famous from disposable alkaline batteries, has found its way into some rechargeable lithium systems too.
Okay. Figure 2.4 compares voltages during discharge for different types. What jumps out there?
The big thing is the high voltage of lithium-ion, right? Typically around 3.7 volts per cell.
Yeah, much higher than others like niacid at 1.2 V.
Exactly. And Petrovic explains this is largely thanks to the organic electrolytes they use. These can handle higher voltages without breaking down, unlike water-based electrolytes, which hit their limit around 1.23 volts before water starts splitting.
And higher voltage per cell is good.
It's a big advantage. Means you need fewer cells in series to reach a target voltage for a device, which can make battery packs smaller, lighter, simpler. The graph also shows that nice flat discharge curve for many types, which is great for stable power delivery.
So what fundamentally limits how well a battery can perform? What are the bottlenecks?
Petrovic lists several key things. Electrode's surface area is huge. More surface means more places for reactions to happen, generally faster rates.
Okay.
The catalytic activity of the materials themselves matters. How good are they at promoting the reaction? Electrolyte conductivity is crucial for ion movement.
Right. Need ions to move easily.
And then you have side reactions. These are unwanted chemical reactions happening alongside the main energy storage ones.
Like what?
They can consume your active materials, build up resistance, just generally degrade the battery over time. A famous example in lithium-ion is the SEI layer solid electrolyte interface. It actually forms on the anode. It's necessary initially, but it can keep growing slowly over time, consuming lithium and impeding performance.
Ah, okay. Unintended consequences. Now, does how fast we draw power affect how much total energy we get? Discharge current.
Oh, definitely. Figure 2.1 shows this clearly. A battery's rated capacity, its nominal value, is usually given for a specific, often relatively low discharge current.
Right.
If you discharge it slower than that, you can often squeeze out a bit more total capacity. But if you discharge it much faster at a high current, the total capacity you get will be noticeably lower.
Why is that?
It's due to various limitations. Reactions can't keep up, ion movement gets restricted, voltage drops more due to resistance. This effect is often described by the Puchert equation or shown in graphs like figures 2.12 and 2.13. High drain equals less total energy delivery.
Okay, that's important. And temperature. That must have a big effect, too.
Huge effect. Figure 2.14 illustrates it. Generally, higher temperatures speed up the chemical reactions.
So better performance.
Temporarily, yes. You might get slightly more capacity or power when it's warm, but the downside is that high temperatures also accelerate those unwanted side reactions and degradation. So long-term, heat is usually bad for battery life.
And cold.
Cold slows everything down, reaction rates drop, ion movement gets sluggish, so you see reduced capacity and power delivery in the cold, sometimes significantly reduced.
Okay. What about just letting a battery sit on the shelf? They lose charge, right? Self-discharge.
Exactly. Self-discharge. It's a slow, internal chemical process that consumes the stored charge even when the battery isn't connected to anything.
How bad is it?
It varies a lot by chemistry. Figure 2.17 shows lithium-ion is generally very good low self-discharge. That's a big plus. Nickel-cadmium, on the other hand, tends to be much higher. Figure 2.1 each shows the capacity loss over time.
Could you get that lost charge back?
Usually, yes, you just recharge it. But Petrovic warns about lead-acid batteries. If you let them sit fully discharged for too long, this thing called irreversible sulfation can happen, and that permanently damages the capacity. You can't just recharge that away.
Good to know. Don't let your car battery die and leave it dead for months.
Definitely not ideal.
Okay, battery life. We hear about calendar life and cycle life. What's the difference? What affects them?
Good distinction. Calendar life is just how long the battery lasts over time, sitting on the shelf or lightly used, just aging, basically.
Right.
Cycle life is about durability under use. How many times can you charge and discharge it before its capacity drops significantly, typically to that 80% threshold we mentioned?
And what impacts cycle life?
Several things, as figure 2.21 shows. The chemistry itself is a major factor. How deeply you discharge it each cycle. Depth of discharge is huge. Deeper discharges are generally harder on the battery, leading to fewer cycles.
So not running it completely flat all the time might be better?
For many chemistries, yes. Temperature also plays a big role. High temperatures usually shorten cycle life. Table 2.3 gives some typical cycle life expectations, noting NiCid can be very high if treated well. Predicting exact cycle life is tricky, though. Lots of factors.
Okay. Now, the infamous memory effect with nickel-cadmium. Is it real? Is it a big deal?
Ah, the memory effect.
Yeah.
Figures 2.20 and 2.22 illustrate it. It is a real phenomenon, mostly associated with older NiCid designs.
What causes it?
It happens if you repeatedly discharge the battery only partially, to the exact same shallow level over and over again. It seems to remember that point. The underlying cause is related to the growth of cadmium crystals on the electrode, which reduces the effective surface area.
So it seems like it has less capacity.
Exactly. But Petrovic stresses it's usually not permanent. It's not an inherent, unavoidable flaw in all NiCid batteries. You can often prevent it or reverse it by doing a periodic full discharge cycle. So its reputation as a major killer drawback is often overblown. Figures 4.14 and 4.15 show more detail on the crystal growth.
Okay, so maybe not as scary as it sounds managed properly. What about internal resistance? You mentioned that earlier.
Right. Internal resistance, think of it as internal friction. It opposes the current flow inside the battery.
What does it do?
Well, higher resistance means a bigger voltage drop when you draw current. So less voltage actually reaches your device. It also means more energy gets wasted as heat inside the battery itself, which lowers efficiency.
And does it change?
Yes. Figure 2.23 shows it often increases as the battery discharges. And figure 2.24 shows it's also affected by temperature, usually high resistance when cold.
Safety. Always important with energy storage. What are the key things to keep in mind?
Petrovic covers this well. Safety depends on a lot of things. The battery chemistry itself, some are inherently more stable than others. The electrolyte type is huge, aqueous, water-based, are generally considered safer than the flammable organic electrolytes in most lithium-ion. The reactivity of the active materials matters. And then how you use it charging and discharging conditions, temperature. Pushing any battery too hard, charging it wrong, or overheating it increases risks, like gas generation, short circuits, and that dangerous thermal runaway.
So, choose the right battery, treat it right.
That's the core message, yes.
Finally then, choosing the right battery. How do you decide?
It's completely application-driven. What's most important? For an electric car, you probably prioritize specific energy, WH/kg, for range, and energy density, WHL, to fit it in the car.
Makes sense.
For grid storage, maybe cycle life and cost per kilowatt-hour are more critical than weight or volume. Table 2.5 is really helpful here. It compares night-sated, NiMH, sealed lead acid, SLA, and Li-ion across various parameters like energy, power, life, self-discharge, cost. Helps you weigh the trade-offs.
Okay, that's a great overview of the fundamentals. Let's zoom in now, as Petrovic does, on two specific, older but still important types: lead acid and nickel-cadmium. Starting with lead acid, main features, uses.
Lead acid, yeah, one of the oldest rechargeable types, still massively used. Think car batteries, SLI starting, lighting, ignition, backup power, UPS systems, some solar setups, PV.
What are they made of?
Lead dioxide for the positive electrode, cathode, sponge lead for the negative, anode, and sulfuric acid as the electrolyte. They have the highest voltage for common water-based batteries, around 2 volts per cell.
And you can tell the charge by voltage.
Roughly, yes, that's a handy feature. Petrovic mentions the evolution from the old flooded type, where you might top up the water.
Right, I remember those.
To modern sealed types, like gelled electrolyte or AGM, absorbed glass mat, which are maintenance-free. Each has pros and cons. But overall, lead acid strengths are low cost, simple manufacturing, relatively low self-discharge, and good ability to deliver high currents, like for starting a car.
So how does the chemistry work during discharge? Figure 3.1.
Okay, discharge. Electrons flow out to your device. At the negative electrode, the lead one, lead reacts with sulfate ions from the acid. It gets oxidized, forms lead sulfate, PbSO4, and releases electrons.
Lead becomes lead sulfate.
Yep. At the positive electrode, lead dioxide, it also reacts with the acid, sulfate ions and hydrogen ions. It gets reduced, takes electrons from the circuit, and also forms lead sulfate, PbSO4, plus water.
So both electrodes turn into lead sulfate.
Essentially, yes, during discharge. And notice, sulfuric acid is being consumed in both reactions, and water is produced at the positive electrode. So the acid concentration goes down. Equations 3.1 to 3.4 detail this.
And recharging just reverses this.
Right.
Puts the lead sulfate back to lead and lead dioxide.
Exactly. You apply external power, force the reactions backwards, regenerate the lead and lead dioxide, and rebuild the sulfuric acid concentration.
What about overcharging, figure 3.2?
Right. If you keep charging after everything's converted back, you start electrolyzing the water in the electrolyte, splitting H2O into hydrogen gas at the negative and oxygen gas at the positive.
Is that bad?
In old flooded batteries, the gas just escapes. You lose water over time, need to top it up. If the level drops too low, plates get exposed. Bad news. Sealed batteries, AGM, gel, are designed to recombine most of that oxygen and hydrogen back into water internally, but they still have limits. You can overwhelm the recombination if you overcharge too hard or too long. Flooded batteries have very low tolerance for overcharge.
Petrovic also mentions additives, like calcium versus antimony.
Yes. These are added to the lead grids that hold the active material. Adding calcium helps reduce water loss, gassing, self-discharge, and corrosion. Good for maintenance-free SLI batteries.
Okay.
Antimony makes the grids stronger, more resistant to the stresses of deep discharge cycles. So it's often used in deep cycle batteries for things like golf carts or solar storage. But antimony can increase water consumption and self-discharge compared to calcium. Trade-offs again.
How are they actually built? And what usually makes them fail?
Construction involves grids pasted with lead compounds, stacked with separators, put in a case filled with acid, and then formed electrochemically to create the final active materials. As for failure, a big one is sulfation.
We mentioned that briefly.
Yeah.
Large crystals.
Yeah, if the battery sits discharged, the lead sulfate can slowly recrystallize into large, hard, inactive crystals. Figure 3.4 shows this. These crystals don't easily convert back during charging, so you lose active material surface area and thus capacity. It's often irreversible if it gets bad.
What else?
Grid corrosion is another major one. The positive grid especially slowly oxidizes and degrades over time, eventually falling apart. Also, shedding of active material from the plates, or shorts between plates. And Petrovic makes a point. Lots of gadgets claim to reverse sulfation, but there's no universally accepted, scientifically proven method endorsed by the industry.
Caveat emptor. The sulfuric acid concentration seems key. How's it change again?
Figure 3.10 shows it clearly. Specific gravity, density basically, goes down during discharge as acid is consumed, goes up during charge as it's regenerated. Figures 3.11 and 3.1 link this concentration directly to cell voltage and the electrolyte's conductivity. And figure 3.13 shows how concentration affects the freezing point. A more discharged battery with weaker acid freezes more easily.
And we can estimate state of charge from voltage. Table 3.1.
Yes. For lead acid, open circuit voltage, when it's resting, no load, gives a decent indication of SOC. Higher voltage means more charge. Figure 3.14 also shows internal resistance increasing as it discharges, partly due to the lower acid conductivity.
What about lifespan? How many cycles?
Highly dependent on usage. Figures 3.15, 3.16, and 3.17 really drive this home. Depth of discharge is critical. If you only discharge it shallowly, say 20–30% OD, you can get many hundreds, maybe thousands of cycles.
But deep discharges?
Deep discharges really shorten the life. And temperature matters too. Higher temps generally reduce cycle life. Self-discharge also happens constantly due to slow reactions with the acid, figures 3.2, 3.21, and it's faster when warm.
Okay, that's a solid look at lead acid. Let's switch to nickel-cadmium. Petrovic says they're often overlooked now.
Yeah, they've been somewhat eclipsed by NiMH and especially lithium-ion, partly due to lower energy density and environmental concerns about cadmium. Cadmium is toxic, so there are restrictions in many places.
What else are the downsides?
Well, the memory effect we discussed, though, may be overhyped. They also have a relatively high self-discharge rate, don't perform as well at very high temperatures, and their charging can be a bit more complex to manage properly.
But they must have some advantages, being the first commercial nickel-based type.
They do. Their big potential plus is often very long cycle life if treated well, sometimes thousands of cycles. They can also handle high discharge rates and offer good performance at low temperatures compared to some others. Robust in a way.
How do they work during discharge? Figure 4.1.
Discharge. At the negative cadmium electrode, cadmium gets oxidized. It reacts with hydroxide ions from the potassium hydroxide, KOH electrolyte, forming cadmium hydroxide and releasing electrons.
Cadmium to cadmium hydroxide.
Yep. At the positive nickel oxyhydroxide electrode, that gets reduced. It reacts with water, takes electrons, and forms nickel hydroxide, releasing hydroxide ions back into the electrolyte.
So the electrolyte concentration stays stable.
Pretty much, yeah. Hydroxide consumed at one electrode is produced at the other. Unlike lead acid, where the acid concentration changes dramatically.
What about overcharging a nice seed? How does it cope, especially sealed ones? Figure 4.2.
This is clever. Sealed nice cells usually have an oversized negative cadmium electrode compared to the positive nickel one.
Why?
So, when charging, the positive electrode gets full first. If you keep charging, it starts generating oxygen gas from the water in the electrolyte.
Okay.
But because the negative electrode isn't full yet and has excess metallic cadmium, that oxygen gas can travel through the separator and react chemically with the cadmium. It recombines, essentially consuming the oxygen and preventing the negative electrode from ever getting full enough to generate hydrogen gas.
So it prevents pressure buildup from both gases.
Exactly.
Wow.
It sets up an oxygen cycle that allows the cell to tolerate a certain amount of overcharge without venting or damage. Equations 4.4 to 4.7 describe these reactions, very important for sealed cell safety.
Figure 4.3 shows the voltage curves. What do we see?
During charge, voltage rises, then kind of plateaus as that oxygen cycle gets going. During discharge, figure 4.6 shows that classic flat profile around 1.2 volts for most of the capacity, then a sharp drop at the end. Very stable output voltage.
Petrovic shows more charge details in figure 4.4. Anything important there?
It shows how voltage, internal pressure, and temperature change during charging. You can see the effects of the oxygen cycle kicking in. Interestingly, for NiSeed, faster charging is often more efficient than very slow trickle charging, which can sometimes worsen the memory effect. Figure 4.5 shows how voltage and temperature changes can be used as indicators to terminate the charge correctly.
How does temperature affect NiSeed discharge? Figures 4.8, 4.9.
Similar pattern to others generally. Higher temps give slightly more capacity initially, figure 4.8. Cold reduces it, figure 4.9. But figure 4.9 shows it gets complex at very high discharge rates, C rates. The interaction between temperature and current isn't always simple.
Petrovic mentions polarity reversal and antipolar mass. What's that about?
Polarity reversal can happen in a multi-cell pack if one cell dies before the others. The current from the good cells can force the dead cell's voltage negative, potentially causing damaging gas generation.
What?
To help prevent this, sometimes a small amount of cadmium hydroxide, called antipolar mass, is added to the positive electrode. If the cell gets driven into reversal, this material provides an alternative reaction pathway to minimize harmful gassing, a sort of safety feature.
Let's talk cycle life for needed again. Figures 4.11, 4.12, 4.13.
Yeah, as figure 4.11 and table 4.1 suggest, the potential is high, thousands of cycles are possible. But, like lead acid, figures 4.12 and 4.13 show it's very dependent on DOD. Deeper is worse, and temperature, hotter, is generally worse for longevity. Treat them well, they can last a long time.
And self-discharge, figure 4.17.
It's definitely higher than lead acid or lithium-ion. Figure 4.16 shows a significant capacity drop over just a few months of storage. They need recharging more often if left unused.
Okay, one last time on the memory effect, with figures 4.14 and 4.15.
Right. These figures reinforce the idea. It's caused by cadmium crystal growth. Figure 4.15 shows that, often triggered by shallow repetitive cycling or long inactivity. Figure 4.14 conditions. But again, Petrovic emphasizes it's usually reversible with full discharge cycles. Not a permanent failure mode in most cases, and modern designs mitigate it somewhat.
And finally, NiSeed components and failure modes.
Components can vary different electrode constructions, sintered, pocket, etc. Separators, usually polypropylene or nylon. Failure modes. Internal shorts are common, sometimes from those cadmium dendrites growing through the separator. Electrodes can passivate, become less reactive. Active material can degrade or shed. Separator can break down. Sometimes the positive electrode swells. Various ways they can wear out.
Wow. Okay. This has been, well, truly a deep dive. We've gone way beyond just knowing batteries power things.
Absolutely.
It's clear there's just a huge amount of complex science and really clever engineering packed into these devices we use constantly and, frankly, often take for granted.
It really is fascinating when you look under the hood. And hopefully, by understanding these fundamentals, the electrochemistry, the different types, all the factors affecting performance, you, the listener, have a much richer appreciation for how they work.
Yeah, and maybe make better choices about using them.
Exactly.
So as we wrap up, here's something for you, our listener, to think about. We've heard about all this complexity, the constant evolution. Given all that, what future battery innovations do you think will be the most impactful? What breakthroughs might really change our daily lives or help tackle big challenges like grid-scale energy storage for renewables?
Yeah, where is this all heading?
Definitely something to ponder. Lots of potential out there.